Welcome back. Number 62 is a very interesting problem because it explores or investigates why certain gases are not present in Earth's atmosphere, or at least one reason why certain gases may not be present, and also why other planets or moons may lack an atmosphere altogether. So I've drawn here a crude planet with an atmosphere around it. My little dots here are supposed to represent particles of air. And I'm realizing after watching my last tablet video that you can't actually see the little cursor representing my stylus. So let me switch over to the mouse. Each of these dots represents a particle of air. And you can imagine that the hotter the atmosphere is, the more quickly these particles will be zipping around back and forth. And they're all colliding with each other. Some of them are moving faster than others. You may have a fast air particle collide with the slow air particle and they exchange some kinetic energy. So the slow one becomes the fast one and vice versa. Just think about pool or billiards. When you strike the cue ball into the other balls, some of them speed up, others may slow down, but there's got to be some overall average speed or really average kinetic energy, which is what the temperature describes. That's what temperature tells us after all. It's a measure of the average kinetic energy of the particles in a gas, for instance. And here's one of the relations that you really should just have memorized from these chapters. The average kinetic energy of a particle in a gas, I'll put the bar for average, or you could write the subscript AVE. Well, it's directly proportional to the absolute temperature, T, and that constant of proportionality is almost Boltzmann's constant, lowercase k, and your book puts a subscript B for Boltzmann. I'm just going to call it lowercase k. And I say that the proportionality constant is almost k because there's also a factor of 3/2 out front. And this is, of course, related to an idea from that I presented in the previous video, that the energy per mole of a monatomic gas per Kelvin is 1/2 capital R. Actually, I left out one per. It's the energy per mole per Kelvin per degree of freedom. But a monatomic gas has 3 degrees of freedom, 3 degrees of translational, I should say translational freedom. And that's what accounts for this factor of 3 out front. Okay, so am I missing anything here? No, this is the average translational kinetic energy. Now, if it's a diatomic gas like nitrogen or oxygen, then there is additional energy associated with the rotational degrees of freedom. But right now, we're just talking about translation. And another way of writing the average translational kinetic energy here, not rotational, translational, would be 1/2 times the mass of the particle. So lowercase m is the mass of the particle times, and I'm being very careful here to enclose v squared in parentheses. So it's the average squared speed. The kinetic energy of a particle is 1/2 mv squared. Well, you've got jillions of air particles here in the atmosphere moving at all different speeds. That means a whole bunch of different kinetic energies. We'd like the average kinetic energy. That's what's equal to 3/2 kT. Well, they all have the same value of 1/2 and the same value of m if we're talking about identical particles. So you could factor that out, so to speak, of the average. And so you're really just looking at the average value of v squared. And that can be written as 1/2 times the mass of each particle times the square of the root mean square speed, VRMS. Subtle difference there. This is the average value of speed squared in parentheses, no parentheses over here. So this is the square of VRMS. So by definition, the RMS speed is the square root of the average value of the square of the speed. See that? First, you calculate all the squared speeds of all the particles. Then you find the average value of those squared speeds, and then you take the square root. That's VRMS. Notice if I squared VRMS, the square root sign would go away, and I would have V squared average. Not V average squared, but V squared average. Subtle difference there. Okay, so we could solve the problem here in terms of VRMS, but I think we're going to find it's easier just to deal directly with the energies. Because here's the idea. You all remember, hopefully, from mechanics that if you launch a projectile away from the surface of the Earth fast enough, then yes, as it moves away, let me get the cursor out. As an object moves away from Earth, it slows down because gravity is doing negative work on it. And usually it slows down to a stop and then it falls back to the surface. Certainly anything that you can throw will slow down and eventually return. Even if you get a slingshot and launch it faster, it's going to slow down, stop, and return. Even if you use a rail gun to launch it with a tremendous amount of energy, eventually it's going to stop at some point and fall back down. But if you gave it enough energy and you didn't have to worry about air drag and vaporizing in the atmosphere, sure, it would continue to slow down all the time. But by the time it got to infinity, which of course is impossible, it's still moving with a significant amount of energy. So it's never going to fall back. There's a certain launch energy that will make it so that the projectile never returns to the Earth. And the speed at which that happens, of course, is called the escape speed. So let's review very briefly how to calculate the escape speed. Escape speed. Here's the whole idea. It's conservation of energy. You say the energy at launch is the energy, same thing as the energy as when the particle gets really far away from planet Earth. I say at infinity. Of course, you can never get to infinity, but let's just imagine launching something away from the Earth and watching it travel away until its distance from Earth is like 1,000 times the diameter of the Earth. By the time you're that far away, the gravity is really, really weak. The force of gravity would be close to zero. Well, we know that as the launched object rises away from the Earth, its kinetic energy will be transformed into potential. Gravity is a conservative force. It does negative work on the projectile, which transforms that kinetic energy into potential energy. So we start out with a certain amount of kinetic energy, and instead of calling it K initial, capital K, I'm actually going to call it K escape. And it's important to understand that this capital K is not K for kelvins. We're using it for kinetic energy. So there's a certain kinetic energy associated with the launch, a fast enough launch to escape from the Earth. And don't forget about the potential energy initially. So I'm mixing my notation slightly, but both of these energies, K escape and U initial, are what the projectile has at the moment it's launched from the surface. And then we've got the kinetic energy final plus the potential energy final. But the idea is, remember we've been using this formula for gravitational energy. There's the mass of the planet that you're escaping from. There's the mass of the projectile itself. And then there's the distance between their centers. This was our new and improved formula from the end of Physics 3A for calculating the mutual gravitational energy of two masses. But once we get to infinity, once we're super far away from the Earth, we're dividing by an enormous distance so large that this is effectively zero. So the idea is once you've escaped from the Earth, you're so far away that your potential energy is zero. And I'll do a quick sketch of that graph of potential energy just to remind you. It looks something like, oops, I wasn't actually supposed to touch the axis there. But it rises, rises, rises. As you move away from the Earth, the potential energy is rising and it asymptotically approaches zero. So when you're far enough away, the potential energy is essentially zero. Now, the idea is if you launch it just barely fast enough to escape, then once it gets infinitely far from Earth, it's got no leftover kinetic energy. It just barely got to the finish line. So the final kinetic energy is 0. Now, if you launched it faster than escape speed, then once your projectile gets 1,000 times as far from the Earth as the Earth's diameter, you'd still have leftover kinetic energy. So not only did you escape, you're still moving fairly quickly, but we just want the cutoff point, the absolute bare minimum of energy required to escape. Okay, so I'm not even going to evaluate K escape as 1/2 mv escape squared, because we'll see that we're really just interested in the energy anyway. But I do need to evaluate the potential energy initially. Let me make sure I'm recording. Sometimes I'm paranoid that I forgot to hit start. Okay, yes, I am. So the initial kinetic energy would be this formula here, evaluated at our starting point. Well, when you launch something, it's from the surface of the Earth. And actually, in this problem, it'll be from the top of the atmosphere. But the atmosphere is so thin compared to the radius of the Earth. It's just a thin shell of gas that let's use the radius of the Earth as our starting distance from the center of the Earth. So negative big G, mass of the Earth, mass of the particle over the radius of the Earth. That's got to equal 0. So in other words, this is the quantity of kinetic energy with which you must endow your launched particle if it is to escape the Earth and never come back. That's ignoring air drag, of course. So the more massive your planet is, the more kinetic energy you have to give your projectile. In fact, they're proportional. Twice the mass of the planet would require twice the initial kinetic energy. And even more intuitively, twice the mass of the projectile, twice the kinetic energy. So if you've got 2 rocks that you want to eject from planet Earth and one rock is twice as massive, obviously you're going to have to give it twice the kinetic energy to escape. And this is interesting. The larger the planet's radius for a fixed mass, the less kinetic energy is required. So if Earth had the same mass, but it was way more bloated, let's say it was like a gaseous planet with a much larger diameter, the gravity would be weaker at the surface and you would not need as much initial kinetic energy in order to escape. Okay, so I probably neglected to describe what we're really being asked for here. The idea is, if the temperature of this atmosphere is high enough, then the average gas particle will have sufficient energy to escape. And of course, we're talking about particles at the in the upper layers of the atmosphere, really the very top, tippy top of the atmosphere, because it doesn't matter if a particle near the surface of the Earth is moving really fast. It can't escape per se because it's going to collide with a bunch of other particles before escaping. So we're really looking at particles at the very edge of the atmosphere that actually have an opportunity to be boiled away from the atmosphere. So maybe there's I'm going to look at this particle right here. Maybe it's not moving quite fast enough, but then it has a collision with an adjacent particle and it gets kicked out with just enough kinetic energy to escape. So the temperature determines the average kinetic energy. If that average kinetic energy is greater than the escape kinetic energy, then any particle with that average energy or greater, which is located at the top of the atmosphere, will be kicked out and won't come back. So all we really have to do is equate this average energy, which comes from thermodynamics or statistical mechanics, equate that with this result from classical mechanics. So we're talking about a result from Newtonian mechanics and a result from 19th century thermodynamics. All right, so minimum temperature for escape. That 3/2 kT would need to equal this. And I could actually write this as an inequality if I wanted and express it as the temperature has to be greater than or equal to some number. So yeah, let me actually do that. I will delete this equal sign here and write it instead as an inequality. Oops, where's my pen? Okay, again, this is the condition necessary for the average particle to have enough energy to escape. That's supposed to be a capital R there. So the absolute temperature must be greater than or equal to, we've got a 2/3 over here now. G big M little m over R K. Now I could do this in my hand calculator. I think I'll do it in Excel because we see that that minimum temperature is going to depend on the mass of the planet we're talking about, the mass of the gas particle. So our atmosphere has a number of different gases in it. And already we can see that that minimum temperature is going to be different for different types of atoms. And it also depends on the size, meaning the radius of the planet. So let me switch over to Excel and we'll see how this temperature, actually, let me do one more thing here. For hydrogen, for example, H for hydrogen, it's really H2, right? The diatomic gas hydrogen. The mass would be, well, remember one nucleon, which is like a proton, like a neutron. I think it's the neutron that's a little heavier. The atomic mass unit, 1U, I think the value your book uses is 1.66 times 10 to the negative 27th kilograms. So a neutron might be slightly heavier than that and a proton slightly lighter. I forget exactly. It's not that important. Well, hydrogen gas, that's two protons or two hydrogen atoms bonded together, and each hydrogen atom has one proton, 1U. So this diatomic form of hydrogen has a mass of 2U. And yes, we are neglecting the mass of the electrons because there's something like 1,800 times less massive. So it's kind of a piddly correction. Nitrogen, on the other hand, well, nitrogen, the atom has atomic number 7. So a single nitrogen atom, 7 protons, 7 neutrons. That would be nitrogen 14, but there's two of them stuck together. So the mass of that gas particle would be 2 times 14 or 28 atomic mass units. So I could, in my Excel spreadsheet, substitute here for some number times the atomic mass unit. And I don't want to use a symbol here like capital N because we're already using N to mean other things like number of moles or number of particles. Here we are in Excel again. I haven't specified units for any of these quantities, so everything's in SI. I happen to know that the radius of the Earth is on average 6,370 kilometers. So that would be times 10 to the third in SI units. And the mass of the Earth, 5.97 times 10 to the 24th. And I know that because I weighed it myself with my kitchen scale. And what is Excel doing? Rounding? I didn't tell you to round. Give us a couple more digits there. And the atomic mass unit in SI, or kilograms, is 1.66 times 10 to the 20th. Did I say 27th earlier? Negative 27th. 10 to the negative 27th. And I'll save that for later, number of nucleons. Big G, 6.67 times 10 to the negative 11th. Boltzmann's constant is 1.38 times 10 to the negative 23rd. And one way you can remember the exponent is to also keep in mind that K, Boltzmann's constant, is related to the reciprocal of Avogadro's number. 6.02 times 10 to the 23rd, that's the number of particles in a mole. The reciprocal of that is related to Boltzmann's constant. So it's no surprise that we've got a 10 to the negative 23rd, if this number is related to the reciprocal of 10 to the 23rd. And I'm really hoping I don't need to enclose the exponent in parentheses because there's that pesky minus sign there. We'll find out. Okay, so here I'm just going to implement the formula that I developed a few minutes ago for the minimum temperature. 2/3 times big G times big M, the mass of the planet, times the mass of the particle, which is going to be the number of nucleons, times the mass of each nucleon. And then we divide by the product RK. Well, I'm going to do it this way. I'll divide by R and divide by K. Right now we get nothing because I haven't entered anything into this cell. So why don't we start with hydrogen? Let's figure out what temperature in the atmosphere is required so that the average typical gas particle has enough kinetic energy to escape from the top of the atmosphere and never come back. Hydrogen gas is diatomic. It's got 2 nucleons because 1 proton for each nucleus. And evidently I did something wrong. 2/3 times B7. Let me just pause and figure this out. Okay, trivial. I forgot to put the equal sign here. It looks like if you want to use this power of 10 notation, you have to have an equal sign up front. And voila, a minimum temperature of 10,000 kelvins would be required to give the average hydrogen gas molecule enough kinetic energy to escape Earth's gravitational field, from the top of the atmosphere. Well, that's super hot. That's way hotter than any place on planet Earth. Remember that for humans, roughly 300 kelvins is comfortable. So that's like 30 times the temperature that we actually exist in. So why don't we have any hydrogen gas in our atmosphere? It's way colder than this temperature here, which would suggest that at the temperature of actual planet Earth, your average hydrogen molecule would have nowhere near enough kinetic energy to escape planet Earth. And it's not like there's any shortage of hydrogen gas in the solar system. After all, it is the most abundant element in the universe by far, followed by helium. So there should be, you would think, plenty of hydrogen gas in our atmosphere, given the fact that the minimum temperature we just calculated is much greater than the actual temperature. So what's going on? Well, let's not forget that at any given temperature, there's really a wide range of speeds that you can find among the particles in a gas. We've already looked at the RMS speed. So 3/2 kT, that's the average kinetic energy of a particle at temperature T. That would be 1/2 m VRMS squared. And of course, if you solve that for VRMS, you get a familiar formula. Hopefully it's familiar. That factor of 1/2 goes away, and we're left with 3 kT over m. Temperature goes up right here. RMS speed also goes up. But the RMS speed is actually, I don't believe it's this speed. This is what you might call the mode of the distribution of speeds. It's the most probable. In other words, if you had like a jillion gas particles all at the same temperature, or that doesn't even make sense. It doesn't really make sense to talk about the temperature of an individual atom. You have to talk about the temperature of that quantity of gas. The most likely speed would be the peak of the distribution here, the Maxwell-Boltzmann distribution. And that's not quite the same as the RMS speed. If I recall correctly, the RMS speed that's supposed to be a dashed line, is slightly to the right, because this distribution, you can see, is not symmetric. It has a kurtosis. That's a fun word from statistics. It's skewed to the right. So these really high speeds over here, notice how low the curve is. There are, the horizontal axis is what's giving us the speed, and the height of the curve tells us the probability or the fraction of gas particles that actually have that speed. Notice that even way out here at 1500 for this particular example, the curve is not quite zero. So there's a very tiny percentage of particles that are going, sorry, you couldn't see my cursor here, way out here. There's a very tiny percentage of particles that are going way faster than most of the particles are going. There's not many of them, but because this curve doesn't really reach zero until you're way out to the right, there's a non-zero percentage of particles that are going much faster than the majority of the particles are going. And where was I going with this? Right, so we're trying to figure out why there's no hydrogen gas in our atmosphere, even though the temperature of planet Earth is way colder than that minimum temperature that we discovered. Well, sure, the majority of the particles have speeds somewhere in this range. And this majority of particles, see, I told you I'd have the writing of a 6-year-old. These majority of particles have nowhere near enough kinetic energy to escape Earth's gravitational field. They're not going anywhere. But because of the shape of this distribution, there are a small number of particles at the top of the atmosphere, even at this much lower temperature of 300 kelvins, that really do have enough to get kicked out and never come back. And over a great period of time, because the Earth is supposed to be something like 4.6 billion years old. Even if it's just a small fraction of particles that are lost every year, let's say, you wait long enough and virtually all the hydrogen that may have been present in the atmosphere at one time has boiled away in some sense. So it's just a very slow loss, I would think. Let's go back to the spreadsheet and see what the required temperature would be for nitrogen to escape, the typical nitrogen particle to escape. The only thing that has to change here is the number of nucleons. And we just looked at the fact that a nitrogen atom has 14 nucleons. So gaseous diatomic nitrogen would have 28. And that temperature is much higher still, 140,000 kelvins. So this is kind of the opposite problem. Well, it's not really opposite, but that's also an extraordinarily high temperature, way higher than any actual temperature on planet Earth. Yeah, this one shouldn't surprise us, right? Because there is abundant nitrogen in our atmosphere. Yeah, so this just kind of corroborates what we would expect. Most nitrogen, the vast majority of nitrogen molecules in our atmosphere are moving much slower than they would need to be moving in order to escape Earth's gravitational pull. So it's not surprising that they're basically all still here. If you could somehow heat up our atmosphere to 140,000 kelvins, then the typical nitrogen molecule would already have enough energy to escape. And those typical particles at the upper layers of the atmosphere would in fact be kicked out and not come back. But we just looked at the fact that you don't even really need that temperature. Even if you had half that temperature, 1/10 that temperature, there's still going to be a small percentage of particles at the tail end of that Maxwell-Boltzmann distribution, which are still going fast enough, despite the fact that the typical ones are not. So that was part A of the problem. To clarify, suppose this gives the distribution of speeds for hydrogen gas at an actual temperature that represents Earth's atmosphere. Again, even though the majority of those particles don't have anywhere near the sufficient energy to escape Earth's gravitational pull, there's going to be a whole bunch at the tail end that do. So in part C of the problem, we're supposed to make this idea a little more precise. And the book says that a reasonable condition for Earth's gravitational pull to be able to contain a gas, that means keep it in the atmosphere, would be that the average kinetic energy per molecule is less than 1% of the required escape energy. You see that? So what you can do is take an actual temperature that represents Earth's atmosphere, calculate the average kinetic energy of a gas particle at that temperature, and as long as that temperature is, as long as that average energy per particle is less than 1% of the energy needed to escape, then you can be confident that the planet will retain that particular gas in its atmosphere. So once again, the average energy per particle, oops, let's go with the thicker line there, which is less embarrassing for me. Average energy per particle is 3/2 kT. That's really the average translational kinetic energy. Remember, if it's a diatomic gas, you've got 2 additional degrees of freedom. But we're talking about translational motion. That's what makes something escape. And isn't it interesting that it does not depend on the mass of the particle, right? Doesn't matter if you're talking about nitrogen, oxygen, argon, something heavier like CO2. At the temperature of Earth's atmosphere, all of those gas particles have the same kinetic energy on average. Now, because they have different masses, that means that their RMS speeds will be different on average. All right, and we've already seen that the escape energy, this is capital K for kinetic energy, not kelvins. The escape energy, what was it, GMM over the radius of the planet. That's the escape energy, not the escape speed. If you wanted the escape speed, this little m would disappear. You'd have a 2 here, and you'd have a square root around the whole thing. So what we'll do now, as suggested by the book, is just look at the ratio of the average energy per particle of gas in the atmosphere, and compare that to the required escape speed. And we'll do that for 2 different gases, nitrogen and hydrogen. And of course, as I just pointed out, the numerator is not going to change. For a fixed temperature in the atmosphere, the average energy is the same whether you're talking about nitrogen or hydrogen. What does change is the kinetic energy required for escape. So let's look at this ratio for those 2 gases. And if one of those ratios comes out greater than 1%, then that's our explanation. It's like, well, if it's greater than 1%, then that means enough of those particles have sufficient energy to escape that over time, they all will have escaped. But if this ratio comes out to be less than 1%, then we can say, hey, so few, probably nitrogen particles, have sufficient energy that the Earth will be able to retain that even over a great time period. Let's implement that idea in Excel. We have to choose a representative temperature. Of course, there's a wide range of temperatures that exist on Earth's surface, but let's go with 20 degrees Celsius, which is room temperature, comfortable for people. So 20 degrees Celsius, and to convert that into kelvins, we'd have to add 273. And the average kinetic energy per particle, translational kinetic energy, is 3/2 kT, where K is Boltzmann's constant. So it's a very tiny quantity of energy in joules, right? The energy of a single atom is practically 0 by everyday terms. Like it's nothing compared to the energy of 1 food calorie, for instance. And then this is the quantity that's going to depend on the mass of particle that you're talking about. The more massive the gas particle, the more kinetic energy it must have in order to escape Earth's gravity. And that's because the more massive it is, the harder gravity is pulling on it. So we saw that this was the GMM over R, big G times mass of the planet, times the mass of the particle, which again was the number of nucleons times the mass of each nucleon divide by the radius of the planet. And even though they're both really tiny numbers, this number is much greater than the energy per particle. So let's look at the percentage now. This would equal the kinetic energy per particle compared to the kinetic energy required for escape. And we'll convert that into a percentage. And I don't want scientific notation, so how do I undo that? Let's see, if I right click on the cell and go to format cells, I don't want scientific notation, just give me a number, please. And one digit would be just fine. All right, only 0.2% of the nitrogen particles in our atmosphere. No, I misspoke. Let me put it this way. The typical nitrogen gas particle in our atmosphere at the actual temperature of our atmosphere has only 0.2% of the kinetic energy required to escape Earth's gravitational pull if that particle was at the top of the atmosphere. That's so much less than the necessary kinetic energy, we can conclude that nearly all nitrogen particles do not have sufficient energy to escape. On the other hand, if we're talking about hydrogen gas, which has only 2 nucleons per particle, 1 in each atom, check that out, almost 3%. No, I almost made the same mistake. Let me put it this way. The average hydrogen gas particle in our atmosphere has 3% of the required energy for escape. Well, if the typical particle has 3%, then there's going to be a significant fraction, even if it's really small, there'll be a significant fraction of the hydrogen particles in our atmosphere which actually do have enough energy, 100% or even more of the energy required to escape. That's the tail end of that Maxwell-Boltzmann distribution. Whereas with the nitrogen, even the tail end of the distribution on the right side, not enough energy to escape. So while we're here, it would be interesting to look at how the results change if we're talking about the moon. Now, the moon doesn't have an atmosphere, so it doesn't make a whole lot of sense to talk about the temperature of the atmosphere, but let's just leave the temperature alone. Let's assume it's, quote, room temperature on the surface of the moon, but update the values of the mass and the radius. So let me look those up right quick. Okay, the moon is considerably less massive at 7.3 times 10 to the 22. That's about 1/100th the mass of Earth, surprisingly. And the radius is 1737 kilometers, something like 1/4 the radius of the Earth. All right, so even for hydrogen gas, look at that. We've got 2 nucleons, so we are looking at hydrogen. If the moon had started out with an atmosphere comparable in temperature to our own, then your typical, at that temperature, your typical hydrogen particle would have a kinetic energy of translation that's 65% of what is necessary to escape. And that means that the typical particle would not have enough energy to escape, but there's going to be a whole bunch of particles at the tail end of the Maxwell-Boltzmann distribution, which do. I mean, this percentage is so much higher than it is for Earth. You can expect that hydrogen gas would have left the moon's surface in a very short amount of time comparatively. What about nitrogen? Is the moon's gravitational pull sufficient to hold on to nitrogen gas in its atmosphere with 28 nucleons? No, even for nitrogen, your typical particle has almost 5% of the energy required to escape from the upper layers of the atmosphere. And that means, again, a significant fraction of nitrogen particles at the tail end of the distribution will have more than enough energy to escape. And eventually they will have all escaped.